Everyone tries to minimize beer foam. Tilt the glass, pour slowly, wait for the bubbles to settle. You're doing it wrong. That foam isn't wasted beer. It's a delivery system for over 100 aromatic compounds that determine whether your beer tastes flat or fantastic. Most of those compounds disappear within seconds of hitting open air, unless they're trapped in foam. Why does the part you avoid matter more than the beer itself? Pour a beer without foam and take a sip. Now, pour one with a proper head and compare. The difference isn't psychological, it's measurable chemistry you can verify yourself. Foam concentrates volatile aroma compounds at the surface of your glass, right where your nose meets the liquid. Every bubble acts as a tiny transport vehicle, carrying flavor molecules from deep in the beer up to where you can actually smell them. When those bubbles pop, they release bursts of aroma directly toward your nose. No foam means those compounds stay dissolved in liquid, trapped, never reaching the receptors that detect them. Research shows foam can increase hop aroma perception by up to 30%. That's not marketing. That's chemistry working exactly as brewers intended it to work for thousands of years. The magic starts with two proteins you've never heard of. Protein Z and LTP1. Both originate in barley grain and survive the entire brewing process intact, from malting, through mashing, through boiling, through fermentation. When carbon dioxide rises through beer, these proteins coat each bubble's surface, creating a thin elastic film that prevents immediate collapse. Without them, bubbles would pop instantly upon reaching the surface. With them, foam can persist for several minutes. But proteins alone aren't enough for stable foam. They need a molecular partner from hops. Iso-alpha acids, the bitter compounds responsible for beer's characteristic bite, bind with protein Z and LTP1, reinforcing the bubble walls and creating the stable matrix that holds everything together. Different beers produce dramatically different foam because their protein and hop profiles vary. A German wheat beer has abundant proteins from wheat malt, creating thick, creamy foam that clings to the glass in decorative patterns called lacing. A Belgian triple has fewer proteins but higher alcohol, which destabilizes bubbles and produces thinner, less persistent foam. Stouts get their dense tan head from roasted malts that contribute specific proteins optimized for foam retention. Nitrogen-poured stouts produce even smaller bubbles, creating that signature cascading effect. The head on your beer isn't accidental. It's engineered through grain selection, hop timing, and fermentation control. Some breweries employ foam scientists whose entire job is optimizing bubble architecture. So if foam enhances flavor and breweries engineer it carefully, why do so many people actively try to eliminate it? The answer is cultural misunderstanding passed down through generations of drinkers. In Germany, a full head signals quality and freshness. Beer halls serve pints with 2 fingers of foam as standard practice, and bartenders who underpour face complaints. In America, visible foam often means the bartender cheated you out of liquid. Bars overpour to minimize head because customers demand maximum volume. But the difference is negligible. A proper head takes up maybe 10% of the glass while delivering disproportionate flavor benefits. You're not losing beer. You're gaining everything that makes beer worth drinking. Here's what happens at the molecular level. Beer contains hundreds of volatile compounds responsible for its complex flavor, but most are hydrophobic, meaning they don't dissolve well in water-based liquid. They want to escape into air. Carbon dioxide bubbles provide the perfect transport vehicle. As each bubble rises, hydrophobic aroma molecules attach to its surface like passengers boarding a departing train. The bubble reaches the foam layer, pops and releases those molecules into the headspace above your glass. Ethyl hexanoate delivers apple and anise notes. Ethyl octanoate provides tropical fruit. Isoamyl acetate creates banana aroma. Without foam, these compounds dissipate randomly into the air. With foam, they concentrate and release in controlled bursts every time you sip. Here's what most people miss. The glass matters more than you realize. A dirty glass destroys foam almost instantly. Residual oils from food, lipstick, or dish soap create weak points where bubbles collapse on contact. A single fingerprint can leave a foam-free streak down your glass. Some premium glasses have laser-etched nucleation points at the bottom, creating continuous streams of tiny bubbles that refresh the foam layer as you drink. Temperature affects foam too. Cold beer holds carbonation better but releases fewer aromatics. Warmer beer produces more aroma release but less stable foam. The ideal serving temperature balances foam stability against flavor expression. Every variable connects to that thin layer of bubbles. Brewers have known foam matters for centuries without understanding why. Ancient brewing texts mention foam quality as a sign of proper fermentation. German purity laws indirectly protected foam by limiting ingredients to those that produce stable heads. Only in recent decades has chemistry explained the protein structures and aroma transport involved. Craft breweries now optimize for foam alongside flavor, recognizing that presentation affects perception. The next generation of brewing focuses on controlled release, designing foam that delivers specific aromas in specific sequences as you drink. What looks like simple bubbles is actually precision engineering. Next time you pour a beer, stop tilting the glass. Pour straight down the middle and let it build a proper head. That foam contains over 100 aromatic compounds the brewing process spent weeks creating. Protein Z and LTP1 survived malting, mashing, and fermentation just to coat those bubbles. Iso-alpha acids from hops bind with them to hold everything together. Every bubble that pops releases flavor you'd otherwise miss completely. The foam isn't waste, it's the finish line. So, how do you pour yours?